I'm focusing on the precision matrix, which is essentially a matrix showing the relationships between variables. The sparsity refers to how many of its elements are zero. A sparse matrix has many zeros, suggesting simpler relationships between variables. A dense matrix, on the other hand, has more non-zero values, meaning more complex relationships. Think of it like a network. A sparse network has few connections, while a dense network is highly interconnected. This is a crucial parameter in the graphical lasso method. I think of it as a tuning knob. A higher alpha means stronger regularization, pushing the precision matrix towards sparsity, more zeros. A lower alpha means weaker regularization, leading to a denser matrix with fewer zeros. I like to say it controls how much we simplify our model by eliminating some connections between variables. The graphical lasso, is a method for estimating a sparse precision matrix. It's named after the lasso regression technique used in statistics. The alpha parameter helps control the level of sparsity that graphical lasso aims for in the precision matrix. The goal is to get a simpler, more interpretable model, rather than one that captures every tiny detail. The key is understanding how this alpha parameter regulates the complexity of relationships in our data. This is the actual question which I will be working on. It's basically assessing our understanding of how graphical lasso works and how changing the alpha parameter influences the precision matrix produced. The problem directly explores the use of graphical lasso in Sklearn, examining the impact of the alpha parameter on the precision matrix. This question asks you to consider the impact of the alpha parameter, which controls the strength of L1 regularization, on the precision matrix produced by Sklearn's graphical lasso. I'll guide you through evaluating the truthfulness of each statement related to this process. Let's break down each statement to understand how alpha affects the results. Think of alpha as a dial controlling the sparsity of your precision matrix. A larger alpha means more sparsity, more zeros in the matrix. This is absolutely correct. Graphical lasso uses L1 regularization, and alpha directly determines how strong that regularization is. Think of it like this. Alpha is a tuning knob that adjusts how much we punish large values in the precision matrix. A larger alpha means a stronger penalty. Therefore, more elements will be driven to zero to reduce overall magnitude. This statement is also true, although not in a perfectly deterministic way. I want to emphasize that increasing alpha generally leads to a sparser matrix, fewer non-zero elements, which is the desired effect of regularization. But the precise number of zeros depends on both the data and the alpha value. It's not a one-to-one correspondence. We can still say there's a direct relationship between alpha and sparsity. This statement is incorrect. Increasing alpha actually makes the precision matrix sparser asterisk, meaning it will have more zeros, not fewer. Remember, we are aiming for sparsity for more interpretability and fewer false connections. This statement is also incorrect. While the goal is sparsity, we will get approximately sparse results, not perfectly sparse. Numerical imprecision might lead to tiny values very close to zero rather than true zeros. I see alpha, as the tuning knob for the graphical lasso. It controls how much I emphasize sparsity in my precision matrix estimate. A larger alpha means I really want a sparse solution, and will push more values to exactly zero or very close to it. A smaller alpha means I'm less concerned about sparsity. I will clarify that it's not a perfectly direct relationship. While a larger alpha generally leads to fewer non-zero elements, making the matrix sparser, the precise number depends on the data and the alpha value. Think of it like this. Alpha guides the sparsity, but the data determines the exact outcome. That's correct. Alpha directly controls the strength of the L1 penalty, also known as lasso regularization. This penalty helps to shrink less important elements in the precision matrix toward zero, leading to a sparser estimate, improving interpretability and reducing overfitting. That's incorrect. Increasing alpha actually does the opposite. It creates a sparser precision matrix. I know it might seem counterintuitive, but it reduces the number of non-zero entries. A larger penalty reduces complexity, essentially forcing it to use fewer features. That's almost correct, but not quite. The goal is sparsity, and L1 regularization gets us close. However, due to limitations in numerical precision on a computer, we might not always achieve values of exactly 0. We get really small numbers, which are effectively zeros for practical purposes. It's approximately sparse, not exactly sparse. This question focuses on understanding how the alpha parameter in Sklearn's GraphicalLasso algorithm affects the sparsity of the estimated precision matrix, which is the inverse of the covariance matrix. I see alpha as a tuning knob. It controls how strongly we apply L1 regularization, a technique that encourages sparsity in our model by shrinking some of the parameters towards 0. Think of it like a volume control. Higher alpha means stronger regularization. This is simply a matrix containing the inverse of the covariance matrix of your data. It tells us about the relationships between different variables. A key characteristic we're interested in is its sparsity. This refers to the number of 0 elements in the precision matrix. A higher sparsity level means the matrix has many zeros, indicating many variables are not strongly related. GraphicalLasso is a technique used to estimate a sparse precision matrix. Alpha is the key parameter that directly influences how sparse the resulting precision matrix will be. It is at the heart of the question. This means if you increase alpha, you'll end up with a sparser precision matrix, more 0 values, implying fewer relationships between variables in the dataset. Think of it like sculpting. The alpha is your tool to carve out a more refined and clearer result. I'm asking you about the GraphicalLasso algorithm in Sklearn and how the alpha parameter affects the precision matrix it produces. The precision matrix is essentially the inverse of the covariance matrix, and it helps us understand the relationships between variables in your data. You got it. Alpha is the key parameter here. It directly controls the strength of the L1 penalty, also known as lasso regularization. Think of it like this. Alpha is a dial that adjusts how much we want to penalize the model for having many non-zero elements in the precision matrix. A higher alpha value means a stronger penalty, leading to a sparser matrix. Yes, this is true, but remember it is not a perfectly direct relationship. A larger alpha generally results in a sparser precision matrix, meaning fewer non-zero elements. It's like turning a knob. The more you turn it, increase alpha, the more sparse your precision matrix becomes, but it's not a precise one-to-one mapping. The data itself plays a role in determining the exact sparsity. We are investigating the GraphicalLasso algorithm and its parameter alpha. The GraphicalLasso estimates a precision matrix, the inverse of the covariance matrix, which represents conditional dependencies between variables. Alpha is a regularization parameter that helps control the sparsity of that resulting precision matrix. The alpha parameter in the GraphicalLasso implements L1 regularization. This means it adds a penalty to the model's objective function proportional to the absolute values of the elements in the precision matrix. This penalty encourages sparsity, pushing many of the elements towards 0. Think of it as a way to simplify the model by removing less important connections between variables. The output of the GraphicalLasso is a precision matrix, a representation of the inverse covariance of your data. The sparsity of this matrix is directly influenced by the value of alpha. A higher alpha value results in a sparser matrix with more 0 values, implying that many variables are conditionally independent, given the others. This helps to highlight the most significant relationships within the data. I see that you are curious about the role of alpha in the GraphicalLasso. Alpha is the key to controlling the L1 penalty, which is a type of regularization. Think of it like this. A higher alpha means a stronger penalty on large values within the precision matrix. It makes the model simpler by pushing less important connections to 0. This is often used for feature selection. L1 stands for L1 regularization or lasso, short for least absolute shrinkage and selection operator. We're asking about the relationship between alpha and sparsity. As we increase alpha, the precision matrix becomes sparser. What does that mean? More entries in the precision matrix become 0 or very close to 0. The strength of this regularization, the impact of alpha, directly relates to how many non-zero entries remain. The higher the alpha, the fewer the non-zero elements. Alpha is a tuning parameter in the GraphicalLasso model. I use it to control the amount of regularization applied to the precision matrix. It's an important control in determining the sparsity of the resulting matrix and hence the complexity of the model. Lasso, or L1 regularization, uses an absolute value penalty on the parameters. This penalty shrinks the coefficients towards zero, which effectively reduces model complexity and improves generalization. This helps to make our precision matrix sparse, meaning it contains many zeros, making interpretation easier.